A flask of helium gas has a temperature of 0 degrees Celsius. If a second identical flask containing an equal mass of helium is 3 times as hot, in other words, it has triple the internal energy, what is its temperature in degrees Celsius? So we have two flasks. Flask 1 is at a temperature of 0 degrees Celsius, so I'll indicate that as 0 degrees Celsius. We know it has a certain mass, we just don't know what the mass is. We have a second flask, which is at some temperature that we don't know. So I'll just put a question mark on that temperature. But the second flask has the same mass, which we don't know. But we do know one thing. We do know that that second flask has 3 times the internal energy of the first flask. So I'll just go ahead and represent that internal energy. I'll just call it internal energy of the second flask is equal to 3 times the internal energy of the first flask. Well, do we know the internal energy of the first flask? Not directly, not in the Celsius scale. But what I do know about the Kelvin scale is changes in temperature are directly proportional to changes in thermal energy. So a change of temperature in the Kelvin scale directly proportional to a change of temperature, a change of internal energy in the Kelvin scale. So I'll just put some constant of proportionality. I don't know what that constant is. I'll just call it K. But what this tells me is as internal energy changes, so does the temperature in the Kelvin scale. If internal energy doubles, the temperature in the Kelvin scale doubles. If internal energy triples, the temperature in the Kelvin scale triples. So we're given a key piece of information. These flasks are pretty much identical, and we know that the second flask has 3 times the internal energy of the first flask. So that means the second flask has 3 times the temperature in the Kelvin scale as the first flask. So I'm going to make use of that. So I'm going to say the temperature of the second flask in the Kelvin scale is going to be equal to 3 times the temperature of the first flask in the Kelvin scale. Now remember, we could convert from Celsius to Kelvin because, or we'll need to convert from Celsius to Kelvin for the temperature of the first flask, and that conversion is given by a temperature in Kelvin is equal to a temperature in Celsius plus 273 Kelvin. So I'll just use a subscript 273 there to remind myself that's in Kelvin, but I want to continue solving this in terms of variables. So this means that the temperature of the second flask in Kelvin, being 3 times the temperature of the first flask because it has 3 times the internal energy, I am going to say 3 times the temperature of the first flask in Celsius plus 273 Kelvin. Now that we have the temperature of the second flask in Kelvin, we're going to need to convert this back to Celsius so we could answer the question. Remember, the question said, what is the temperature of the second flask in Celsius? So I'm going to use this conversion, that the temperature of the second flask in Celsius is its temperature in Kelvin minus 273 degrees Celsius. So this means that the temperature of the second flask in Celsius is 3 times the temperature of the first flask in Celsius plus 273 Kelvin minus 273 Celsius degrees. So I like to work things out algebraically as far as they can go before plugging in numbers. That's just in general a thing that I like to do. It's good practice, even though you're probably feeling we could plug in numbers here right now. I'm going to leave it until we've come as far algebraically as we can. And I think we have now come as far algebraically as we can. So let's now plug in values. So 3 times the temperature of the first flask in Celsius degrees. So the temperature of the first flask we were given was at 0 degrees Celsius, plus 2 times 273 degrees Celsius. So this gives us an answer of the temperature of the second flask in Celsius is 546 degrees Celsius. The things to recall on this, the main concept we applied on this is the fact that changes of internal energy are directly proportional to changes of temperature in the Kelvin scale. In using that, since we had two identical flasks with their only difference being the amount of thermal energy we had, and since we knew the second flask had 3 times the internal energy as the first flask, I was able to recognize that the second flask has to be at 3 times the temperature of the first flask in the Kelvin scale. So I used that fact to set up our problem to solve for our temperature in the Celsius ultimately being 546 degrees Celsius.